Good morning to all of you. Today we will be continuing our discussion on Rankine cycle, which we started last class. It is an ideal vapor power cycle, well, where the working system is water which changes its phase while passing through the different processes of the cycle or executing different processes of the cycle. And we have also recognized that this Rankine cycle is an ideal reversible cycle with water as the working system which changes its phase executing different processes, and this is a theoretical cycle of a steam power plant. We have also recognized the different components of a steam power plant and what are their basic operations or intended operations, and the cycle has been designed, or the power plant has been designed in such a way that the ideal processes in each and every component should follow the processes of the Rankine cycle. That means the cyclic process executed by the working fluid water. In steam power plant, working fluid is water which receives heat in the boiler, then it is converted into steam, then it is expanded in the turbine. We have already studied this, the just basic purposes in different components. Then the wet steam at the exhaust of the turbine is condensed in a condenser where circulating water takes the heat from the steam and then it is being pumped to the high pressure to the boiler. So therefore, these different processes should follow the processes of a Rankine cycle, and the cycle in the power plant should follow ideally a Rankine cycle. So therefore, Rankine cycle is the theoretical cycle of the power plant, or other way you can tell the power plant has been thermodynamically designed so that its cyclic operation or cyclic process should be the Rankine cycle. Now why then therefore now from this probably we appreciated the understanding of Rankine cycle. Now see that if we try to understand the different influence of different operating parameters on the power plant, what is the goal of an engineer? That if there is a power plant, he wants to find the operating conditions at which the power plant will run at the maximum efficiency. That means we will get the maximum work at the cost of the minimum input energy, which is basically the input means the chemical energy of the fuel. Well, that is being converted into thermal energy which we call as heat, and then that is being converted into work. So to know the influence of the operating conditions, what should be the operating parameters at which the thermal efficiency of the plant will be maximum, we must study the theoretical cycles and what are the influences of the operating parameters of the theoretical cycle on its efficiency, because the qualitative trend will be same. To understand, though this theoretical cycle is an ideal cycle, you can argue that in practice, this is a concept actually. In practice, the cycle differs from the theoretical cycle. Today we will be discussing that. But nevertheless, if we analyze the influence of any operating parameters, for an example the boiler pressure, on the efficiency of the power plant, of the cycle, Rankine cycle, the qualitative trend will be same as that in practice. Whether it will increase with the increase in pressure, whether the efficiency will increase or not, this qualitative trend will remain the same. That is why it is of utmost importance to study the theoretical cycles. So with this I will start again, just recapitulate the Rankine cycle, that this is the Rankine cycle. This is the Rankine cycle in TS diagram, and let this be the boiler pressure, and we consider this is the saturated steam, and let this be the condenser pressure, and this is the boiler pressure in the liquid line. So we appreciated that let the entry to the turbine is superheated. So 1, 2 is the turbine expansion, 2, 3 is the condenser. So in this direction, condensation of the steam. So this is the feed pump, and this is the 4 to 1 is the boiler. So if we again recapitulate this boiler, the basic component, then it comes to a turbine. Well, this is the turbine. From turbine exhaust, where does it go? It goes to a condenser, very simple. It goes to a condenser. So this is turbine T. This is condenser where the circulating water flows and takes the heat from the steam to condense, and this, sorry, I am extremely sorry, there is a feed pump FP. So this is the process. So if we just designate the point 1, 2, then this will be this like this is the inlet to the turbine 1, this is the point 2. So So therefore, this is the point 3, 2 to 3 is the condenser, 3 to 4. So just we have discussed now this last class. Now you see, in practice there are certain losses which are inevitable, because of which this diagram alters slightly in a different look to a different look. What is this? First of all, turbine. If we consider this turbine, usually this process is considered to be isentropic, which means the process should be reversible and adiabatic. There should not be any dissipation. That means it is free from friction. There should not be any thermal dissipation also. Now, to avoid the thermal irreversibility, we can make the turbine insulated, but sometimes even with proper insulation there is some heat loss from the turbine. Well, but one thing we cannot, but that we can minimize to a great extent by properly insulating it. But what we cannot at all minimize is the friction. That means we cannot ensure that this will be an frictionless flow, frictionless expansion, that is an reversible expansion. Here we get the work, this also we should write. Here is WP, here is the heat added to the boiler QB, which the nomenclature which we use. Now you see again, so therefore this process will not be an reversible adiabatic process. So it will be an irreversible process. To the best it can be an adiabatic process, but an irreversible process. So therefore irreversibility in the turbine has to be taken care of, which is the internal irreversibility. Now if the process is irreversible but adiabatic, we can consider it as an approximation that adiabatic but irreversible process. That means not an isentropic process. Then the 1, 2 will not be represented by a vertical line in TS diagram. So what will be its nature? That means what will be the type of this curve? Will it incline to the right or to the left? Right. So it will be inclined to the right, so that the actual process, which is not a reversible, that is why I show it by a dotted line. So this 2 dash is the actual process. Usually we donate the 2 as the actual process, that is the convention. 2s, then in that case we denote here, for example, here now 2 dash is the actual process. Why it inclines to the right, not to the left? Entropy will increase. Why entropy will increase? Because of the increase of entropy principle, because the entropy change of the system in the turbine equals to the entropy change of the universe, since we consider the process to be adiabatic. That means an irreversible adiabatic process, the entropy change has to be greater than 0, because it is an isolated system where the process is real process, so that delta is greater than 0. So therefore it will incline to 2 dash. Similar is the case in feed pump. If there is an irreversibility in the feed pump which is properly insulated, then the process 3, 4 will end like this. So this will be 4 dash. You see, 3 to 4 dash. Now if we now write the expression for WT, considering the turbine as the control volume, then what we get? This is H1 minus H2 dash. So this is the actual work done. But if we consider the process to be isentropic, that is the ideal work, then the ideal work done, that is WT ideal, is H1 minus H2. Now you see, this H2 dash is always more than H2. If you draw this diagram in HS diagram, that will be clear. I draw it in a small scale, the HS diagram. If you draw this thing in HS diagram, that means this is the pressure, this is the pressure line. So this is the line where this is the condenser pressure. So if you draw this thing, this is the H and S. If you draw this diagram properly, this is a line where, so this is the point, this is 2, this is 2 dash. So H2 dash is always more than H2. How do you explain this physically? Obviously, because of the irreversibility, the friction is converted into intermolecular energy. So intermolecular energy increases the temperature, and when the temperature increases, the enthalpy of the working system will increase. So therefore the enthalpy is increased, which means WT is less than WT ideal. That means the work produced by the turbine will be less than that of the ideal work. And this is defined, the ratio of these two is defined as isentropic efficiency of the turbine. Sometimes we define it as simply eta T. T is for turbine. So, this becomes equal to the actual work divided by the ideal work. So, if we know the isentropic efficiency of the turbine, then we can find out the actual work if I know this ideal work. Ideal work we can know from the tables, because ideal work corresponds to the process which is reversible adiabatic, isentropic process. So, therefore, a parameter eta isentropic which gauges its performance regarding the reversibility, that means how much irreversible the process is and how much the actual work deviates from the ideal one, is determined by this eta isentropic. And if we know this thing, we can find out the actual work. Similarly, in case of compressor, what will happen? The actual work feed pump, sorry, not compressor, feed pump, these are the similar things. Turbo machines you will read, when it handles liquid then it is called pump, when it handles compressible flow it is compressor. So, 3 to 4 is the ideal work, but actual work is H4, that means this is the work needed. This is the work needed, but what is the actual work? Actual ideal work is ideal work needed is H4 minus H3. In this case, if you draw this diagram here in the liquid side also, you will see this is just the reverse. That means 4 dash and 4. So, 4 dash has a higher enthalpy than the enthalpy at 4, which is like this H4, 4 dash is more than H4. So, therefore, we see the actual pump work. This you know earlier we did from the control volume steady flow energy equation, considering a control volume enveloping the feed pump. So, in this case what happens, the feed pump work required is more than that of the ideal. That means, here in case of turbine we had less work because of irreversibility. In case of pump is the same thing, we have to put more work than that required by the ideal process. In both the cases we are suffering a loss, and this is defined as the isentropic efficiency of the compressor. Isentropic efficiency of the compressor is defined as the ideal work requirement divided by the actual work requirement, so that it is always less than 1, defined as 1. That means, if we know the isentropic efficiency of the feed pump, we can find out the actual work requirement, which is more than the ideal work requirement. So, it is defined in this way, so that both the definitions give the value of beta less than 1. Under ideal conditions, the isentropic efficiency of turbine and compressor both become 1. All right. Now, there are other losses which are not that prominent as the losses in compressor, turbine and feed pump, because when you consider an isentropic process in feed pump and turbine, this is really a drastic assumption. It is too much a theoretical process, because no process can be accomplished without friction as the mechanical dissipative agent. So, friction has to be there, is inevitable. So, therefore, there is a lot of irreversibility which makes the process irreversible and like this. But other processes we can maintain as close as possible. For example, here if you see the boiler, the ideal process is which is envisaged is a constant pressure heat addition. That means, from 4 dash for example, we add heat at constant pressure. This is the heat addition process, that is QB. And in a steady flow process, there are various components in the boiler through which the steam passes. There are a number of tubes, headers through which the steam passes, and ultimately is converted into water process, converted into steam, and steam is taken up. So, under a steady flow conditions, the pressure drop that takes place. So, usually in a steady flow condition, I have told there is no pressure drop until and unless friction takes care. That means, without friction, if a fluid flows in a steady flow process, there is no pressure drop. So, therefore, the pressure drop because of friction has to be taken care of, so that this process does not become a constant pressure process, but that is not very high if you consider its value relative to the boiler pressure, so that one can neglect it. However, one can show it in the diagram in this fashion. Apart from that, if you make the boiler insulated, that means this we show this QB added from outside to denote this thermodynamic cycle, ideal cycle. Actually, what is happening within the boiler, the fuel is fed and it is being burned and heat is generated and it is being supplied to the working system. So, therefore, the entire boiler, if it is insulated, that means no heat goes out of the boiler. You understand, this heat is coming outside, means this is outside to the working system, water, and this heat is actually generated within the boiler itself. So therefore, if we consider the boiler to be ideal, so insulated, then there will be no heat loss, but in fact there will be certain heat loss from the boiler. So this is shown like this. So because of this, there is a certain loss in pressure, and also let this is the pressure line, very much loss in pressure and certain decaying, rather this is the point, actual one point, decay in temperature also, decrease in temperature. So this point 1 is a point which is at a lower pressure than the boiler pressure P1, and which is at a lower temperature than the boiler temperature T1, and this is thermodynamically expressed as two processes. This pressure drop due to friction is expressed as if a throttling process from 1. That means you draw a throttling process like this. So this is a throttling process 1 to 1 dash, and then at constant pressure cooling to this point 1 double dash. That means I draw it in a larger scale so that you can understand this better. It is not very important, but you must know that how this is being represented if we want to represent it. That means if the boiler pressure drop and heat loss is being represented, let us draw it in an exaggerated manner. Let this is the point 1, and let forget this is this part. So now it is assumed that the boiler pressure drop is this. Let this is the pressure drop in the boiler, and there is a considerable, not considerable, sorry, there is a marginal, sorry, temperature. This is T1 and this is P1. So this point comes somewhere here. Actual, this is the point 1, the actual point comes here. Let 1 double dash. So this 1 double dash point suffers a change in pressure and change in decrease in pressure and decrease in temperature. This is theoretically represented like this, as if we consider an isenthalpic process. This is an isenthalpic process. H is equal to constant. Isenthalpic process which drops the pressure from 1 to, let this point is 1 dash, and then as if there is a constant pressure cooling from 1 to 1 double dash. That means this point which suffers a loss in pressure and a loss in temperature, decrease in pressure and temperature, is constituted by constituting two processes. One is isenthalpic process through 1 to the reduced pressure, which is H is equal to constant line, which cuts this point, and a constant pressure cooling. This is this is simulated by these two processes, so that this becomes the inlet point of the to the turbine, that means outlet to the boiler, and accordingly we can determine this process, or the actual process is like this. Okay. So these are the typical losses that take place in a power plant which can modify the Rankine cycle, and I will now tell that in the condenser there is no pressure drop for the working system, because it changes its phase, and phase change takes place only at the constant pressure. And if it is heavily insulated, that means only heat that is being taken is that by the circulating water, no heat is lost to any third body, so that we can very well represent by a constant pressure cooling line. All right. So these are the places, that is the turbine expansion, pump compression, and the boiler heating up process at constant pressure, where we can modify according to the losses in actual power plant processes. All right. Now the most important part, we will come to the most important part of this discussion, that how to increase the efficiency of a Rankine cycle. Again and again I am telling you, from the beginning I am telling that why you will read Rankine cycle, because this is the first thing which comes in our mind, that why you will unnecessarily read a theoretical cycle, because theoretical cycle is never possible, ideal cycle, ideal processes are never possible, and why you will understand, why you will unnecessarily put our effort to know what is the influence of this parameter, that parameter, pressure, inlet temperature, inlet pressure on the efficiency. We understand efficiency is the output parameter. Why? This is because this theoretical cycle, this cycle or theoretical cycle is the cycle or the theoretical cycle on which the power plant is designed. So the actual cycle may differ from the theoretical cycle. Okay, and any parameter predicted from the theoretical cycle under an operating conditions may not quantitatively match with that of the actual cycle, but the qualitative trend, try to understand, that means the qualitative influence of any operating parameters on the output parameters will be same for both the cases. That is the reasons we study this. Okay, if a theoretical cycle analysis tells that an increase in boiler pressure will increase the thermal efficiency of the plant, the actual cycle will not tell the reverse. You understand, so that we can understand that it has to be increased. But the quantitative result, that means the increase of boiler pressure from some value, if you double it, the increase in efficiency will be something that may not be, that may not match, okay, ideally. So therefore, if we read, therefore we are now interested to know what is the influence of different operating conditions on efficiency, thermal efficiency of the plant, which is the only important parameter for thermodynamic design. Now, let us see, let us consider a case that a ideal cycle. Let us first consider an ideal cycle. Okay. So, this is the cycle. All right, this is the cycle. So, this is the point 1, point 2, point 3, point 4. Now, we see in this cycle that heat addition process is here, where heat is being added. All right, here it is the heat addition process. That means this is QB, and heat rejection process is, what is heat rejection process? This is QC. Now, we know the efficiency of any ideal cycle can be expressed, because we can express the efficiency here in terms of the H1, H2, H3, H4 all values, but we start with that. From the Carnot theorem, we know the efficiency of any reversible cycle is 1 minus temperature of heat rejection, which is here T2, divided by temperature of heat addition. But whenever we define this thing, that eta is 1 minus temperature of heat rejection by temperature of heat addition, we always imply this is the mean temperature of heat rejection divided by mean temperature of heat addition. Usually the heat rejection temperature in all practical cases almost constant, become almost constant. This is because usually the heat is rejected into the atmosphere where the ambient temperature is constant, and in case of power plant it is rejected at a different temperature, lower than the ambient temperature, but the temperature remains constant because it is a phase change heat transfer. So therefore, the temperature of heat rejection is the temperature of heat rejection, which is constant, but temperature of heat addition is the mean temperature of heat addition, which we have already discussed earlier, Tm1, which is the temperature like this. This is the mean temperature of heat rejection. That means we have discussed this thing. This is the mean temperature Tm, which makes this rectangle, the area of this rectangle that is on this S axis, same as this one. That means which give the same heat transfer and same entropy change if it is transferred at that mean temperature, which is some mean between 1 to 4. This is clear. Now, from here onwards we have to think. Now, we know that efficiency therefore can be expressed like this. To increase the efficiency, there are two ways. Either we can decrease this or we can increase this, obviously. So, efficiency, thermal efficiency of a reversible cycle can be increased if we decrease the temperature of heat rejection or if we increase the temperature of heat addition. But temperature of heat rejection cannot go below a certain limit that I will describe afterwards. So, temperature of heat rejection is usually fixed by certain characteristic feature or certain constraining fact. Now, we can increase the temperature of heat addition. Now, we can think over it, how we can increase the temperature of heat addition. Afterwards, I will come why the temperature of heat rejection cannot go below a certain limit. Similar way, temperature of heat addition also cannot go beyond a certain limit. Now, you see that. Now, how can we increase the mean temperature of heat addition? One way of obtaining it, to increase the temperature of the steam to a high degree of superheat. You understand? So that as you go on increasing the maximum temperature T1 along this curve, so you will get an increase in the mean temperature. Mean temperature will increase if you increase the maximum temperature to the cycle. You can go on increasing the inlet temperature to the turbine. But there is a limit for increasing this temperature. This limit comes from the, because you cannot go on infinitely increasing this temperature to a very high value. This limit comes from the practical consideration of turbine blade materials restriction. That means practical consideration or practical restriction imposed by the turbine blade materials, which cannot withstand certain temperature, above certain temperature, which cannot withstand a temperature above a certain value. And moreover, this temperature depends upon the working system. Now, the steam, which is not a very highly superheated gas, it contains moisture, but when it is superheated, moisture also is not there. But because of certain properties of the steam, this temperature usually it has been found from the metallurgical consideration of turbine blade should not be made more than 600 to 700 degrees Celsius, so that we cannot go 1000 or 2000 degrees Celsius, the turbine blade material cannot withstand. So therefore we see there is a automatically temperature restriction which is 500 to 700 degree. So this restriction is there, that means I can draw a line, that means this is my restriction, that is the maximum temperature which I can go. Let this be the T max, that is the maximum temperature which maximum temperature of the cycle, that means the maximum temperature of the cycle is limited by the turbine material considerations. Now therefore we see that we cannot go beyond this, but we can even go beyond this temperature. Now if this is the temperature, then the not beyond this is the temperature, then this is the maximum, this is the mean temperature of heat addition, that means the point will be here, the point is 1 dash. So the mean temperature of heat addition is increased, which is something between 4 to 1 dash. Now if we want to gain more for Tm1, the mean temperature of heat addition, we can have another thing, that means we increase the boiler pressure. That means we cannot increase the mean temperature of heat addition more than that which is obtained for point 1 dash and 4, okay, because if we go beyond that, the temperature restrictions will be violated. So we have temperature more than that which can be which will be withstood by the turbine blades. So therefore we can increase till this inlet the average temperature of or mean temperature of heat addition if we increase the boiler pressure. That means if we consider a boiler pressure like this, and for the same, that means we make the point here 4 dash, here now 4 dash nomenclature goes. Now if we increase the boiler pressure, so the cycle will change, that means this will be our 1 double dash, for example. So instead of going 1 dash, that means earlier I started with 1, I went to 1 dash at the some boiler pressure, existing boiler pressure, that is the maximum, the temperature limit. That means I set the maximum temperature to the, that I set the maximum temperature of the cycle to them, to the maximum temperature which can be withstood by the turbine blades, and at the same time I go on increasing the boiler pressure, so that the mean temperature of heat addition is increased. Why? This is because you see, though the maximum temperature is same, the temperature range through which the water is being heated is now increased, because this temperature is more than this temperature, and throughout on this curve the temperatures are more. Here also these temperatures are more than this, saturation temperature at this pressure will be more than this. You understand? For example, let this is 10 atmospheric pressure and let this is 15 atmospheric pressure. So obviously the saturation temperature is more, so the temperature in the cooling water, the liquid water region is more. So therefore the mean of 1 double dash and 4 dash is more than that of 1 dash and 4, though 1 dash and 1 double dash are same. That means setting the same maximum temperature, because of the metallurgical restriction, I can increase the boiler pressure and I can increase the Tm1. But where now the limit comes? But increasing the boiler pressure. So there has to be again everywhere you see we cannot monotonically go on increasing an operating parameter to gain the efficiency. So there is a point where you have to stop. This comes from two ways. By two ways. One is that efficiency curve will show that after some increase this will automatically fall. We cannot go, there is an optimum value we reach. That is number one. Another one, if we do not have such optimum value for the efficiency, where operating parameter has to be set that beyond which the efficiency will fall, even if there is a monotonically increasing trend, we get that natural restrictions imposed on the maximum value which has to be set for this type of gain. Here now, as you see that if we increase this boiler pressure, what happens for the same temperature, if I drop a line, if I drop a line here, this will meet here. But if I drop a line from here, this will meet here. So if I go on still increasing the boiler pressure, if we consider another boiler pressure with the same temperature, the line comes here. So now what is changing now? You see, at the end of the expansions, what we get? The dryness fraction is reduced. That means if we increase the boiler pressure, that means that the inlet point to the turbine, if the temperature is kept constant, which is set already as the maximum temperature, can be withstood by the turbine blade. But if you go on increasing the boiler pressure to have an increase in the mean temperature of heat addition, what we sacrifice is the dryness fraction at the end of the expansion process in the turbine. But why I use the word sacrifice? This is because if we consider the turbine, so from the boiler, when it comes here and goes here, then this goes to the condenser and again to the feed pump. Now you see, at the end of the expansion process, the dryness fraction is drastically reduced. Now there is a limit to this minimum value of the dryness fraction. Turbine is composed of several stages. There are rotating blades. There are blades fixed on a rotating disc, which are known as stator elements. There are fixed blades, fixed blades which are fixed to the casing of the turbine, known as stator blades. So these are the components of the turbine. So there also the blade materials suffer a tremendous loss due to erosion of the water particles. So amount of water particles increase when the dryness fraction is decreased. That means the quality is decreased. That means moisture content is increased. That means with an increase in moisture content, when the steam at high velocity impinges the steam blades or passes or glides along the blade surfaces of this steam turbine, they have a detrimental effect due to both combined effect of erosion and corrosion, for which the turbine blade life gets deteriorated. The same thing, the material restriction comes. As for the high temperature, beyond certain temperature of 600 or so 700, the turbine blade materials, the life of the turbine blades gets drastically reduced. Similar is the case that if the moisture content at the end of the expansion in the turbine gets increased over a certain value, or the dryness fraction gets decreased over a minimum value, then the turbine blade material gets drastically reduced. So therefore you see, from the viewpoint of the material life of the turbine blades, we have a restriction on the maximum temperature on the cycle and a minimum dryness fraction at the end of the expansion. Not only at the end, if you follow this line, throughout this expansion the dryness fractions are less. Throughout the expansion, dryness fractions are less. That means throughout the expansion process, dryness fraction will be above certain values. So that limitation is imposed on the end process. That means dryness fraction at the end of the expansion. All right. So therefore these two things makes, or because of these two things, the maximum temperature and the maximum pressure get fixed. Clear to everybody? So we know that an increase in Tm1, the inlet temperature, mean temperature of heat addition, will increase the efficiency, but we cannot go beyond. Now regarding this, the minimum temperature, I tell you, the usual temperature is sometimes around 40 degrees Celsius. What happens, you see that if you go on decrease, this question is sometimes asked, I will ask you this question in Bhayavosi, that why a condenser is used in a steam power plant. This may be taught in steam power plant, but this is a very important question in thermodynamics. Why do you use a condenser in a steam power plant? Sometimes so people will tell, when you will read the power plant, the very simple answer comes there. We know in a power plant the water has to be condensed and has to be fed back to this pump, which is known as feed pump. So even if you do not condense this water, so how we can feed this water to the boiler? Through the feed pump. We require the water to be fed back. Then the question is that why don't you waste this steam in the atmosphere, condense it, and we have a water lake, or we have a pond, or we have an abundant supply of water nearby from where we can feed the boiler afresh. Then the next question comes when you read the power plant. This will be your inevitable questions which come first in your mind. These are the practical questions. Said the water has to be treated properly, because that water should not contain certain things which is detrimental to the boiler tube materials, which will be taught afterwards. So treated water has to be there. Then I give you the answer that okay, and water treatment plant is there, which is a free gift and whose maintenance is free, so you don't have to bother with this water treatment. Consider the water is already treated, and treated fresh water is abundant in supply. Even if we will have a condenser to close this circuit to feed this pump with the feed water, then the student cannot answer it, because the answer lies in the thermodynamic concept. Why do you require a condenser? Now you come here that if we decrease the temperature of heat rejection, then we get an increase in the efficiency. Now if you condense it at atmospheric pressure, then this temperature is 100 degrees Celsius. That means this temperature is fixed by that value, that is the saturation temperature corresponding to the atmospheric pressure. Now if you can condense this steam to a pressure below the atmospheric pressure, you can reduce the temperature of heat rejection. That means if you go on subatmospheric pressure condensation still lower than the atmospheric pressure. What you do, the temperature of condensation is also low. For example, if you go to a pressure of 0.1 atmospheric pressure, roughly, I am not sure, 0.1 or 0.09 atmospheric pressure, where the saturation temperature is 40 degrees Celsius. That means you are capable of making it 40 degree. Whereas if you condense it at atmospheric pressure, your value is 100 degree. That means you are gaining an efficiency if you reduce the pressure, that is the back pressure. This is known as back pressure. That means the pressure at which the steam should be condensed to a subatmospheric pressure. It is clear. So to condense the steam at subatmospheric pressure, we will have to design a closed heat exchanger, and we will have to maintain a vacuum there by arranging some arrangement, by arranging something by which the air can be withdrawn from the condenser by an vacuum pump which withdraws the air from the condenser to maintain a certain degree of vacuum. So therefore a condenser is required. Condenser maintains that, and there is a circulating cooling water which is supplied to the condenser tubes, which takes the heat from the condenser. The condensers will again be taught in power plant. I am not going into detail of it. There are a number of tubes through which the circulating water flows, and on the surface of which steam is condensed. So therefore the basic purpose of condenser is to reduce the pressure of condensation, or to make the condensation possible below the atmospheric pressure, so that the temperature of condensation is reduced, so that the temperature of heat rejection is reduced, and we get a gain in the thermodynamic efficiency or the thermal efficiency of the plant. Now question comes up to what level we can go. Now very first question which comes into the mind of an engineer, probably the minimum level of the pressure will come from the restriction of the vacuum pump. That restriction of the, not the vacuum pump, I am sorry, the restriction of the air infiltration to the condenser. That means if you go on increasing the vacuum, more air will come, ultimately you will not be able to maintain a vacuum to a very high degree. But it is not so. Even above that a restriction comes. What is that? Now you know, for cooling this is very important. I am telling you, I will ask this question in an interview when you may face me, that when the cooling water which is being circulated within the condenser, that is taken from atmosphere, so it has got the temperature which equals to the ambient temperature. Let this temperature is 20 degrees Celsius. So usually there is a rise in temperature. Usually there is a rise in temperature in a condenser, in a power plant by 10 degree or like that. Let this comes at 30 degrees Celsius. Now we will have to consider the steam which is being condensed must be at a temperature little higher than these two temperatures. That means little higher than 30 degrees Celsius, otherwise heat will not flow. That means steam has to condense. You want to condense certain amount of steam. So coolant temperature has to be low, because heat transfer is possible only if there is a negative temperature gradient. Heat flows from a high temperature to low temperature. That means by chance you create a vacuum whose value is, for example, 0.05 atmospheric pressure. You are very thrilled, and you see that the saturation temperature is 20 degrees Celsius. So you are very thrilled by seeing this equation, efficiency is enhanced by a great amount. Then you pump the circulating water, steam is not condensed at all. You understand? Because the steam temperature is lower than the cooling water temperature. Steam may get heated, it may be dried up also. So therefore the temperature, saturation temperature corresponding to the pressure at which the steam is condensed must be higher than the available cooling water temperature. Very important. So that sets the limit of the pressure, and accordingly the temperature of the practical cycle. So here ends my discussion on the influence of the operating conditions like inlet pressure, inlet temperature, condenser pressure, condenser temperature on the thermal efficiency, and how do they behave in a sense that how the thermal efficiency increases with the change in this T2 and TM1. All right. Now I come the concept of reheat. Concept of reheat. Concept of reheat. Now we have already recognized again and again the same diagram. Now we will go on. We have already recognized that a higher boiler pressure cannot be used. Why? This is because we can, for example, here again I show it like this. Higher boiler pressure cannot be used. For example, if this is the line, just here I show, for example, this is the X is equal to 0.85, and usually this is the value, 85% dryness fraction, which is taken as the minimum value at the end of the expansion. That means the feet of the expansion should be the cutting point of this X is equal to 0.85 lines and the condenser pressure lines. Correct? Okay. Now, if we increase the pressure, for example, so therefore this should be the maximum pressure, this P1, because if we increase from this P1, this value gets shifted towards the left. Clear? That means if I am told that 85% is the minimum dryness fraction at the end of the expansion, and if this Tmax is your temperature, for example, this is 600 degrees Celsius, that means my pressure is fixed by this from the geometry. That means I can draw this line which cuts this constant temperature. I give this is my isobaric line. That means this is the pressure. But I can not use this high pressure steam because we cannot increase the pressure. This point will come here, but I can do so. How? Now, if we start with this point, that means if we increase the boiler pressure, heat the water at higher pressure, evaporate it or boil it, then again superheat it and start with this point even, but don't go throughout from this point to the condenser pressure, but you expand up to some point here, for example. Then you take this steam to an heat exchanger for heating it, which is known as reheating. That again heat the steam at that constant pressure, reduced pressure up to it. That means the first expansion takes place from the initial pressure, not to the condenser pressure, to an intermediate pressure. Let this is the intermediate pressure. Well, then heat it again to the initial temperature. Sometimes it is not heated to the initial temperature, but we will consider in an ideal case it is heated to the initial temperature, and then if we drop it, then we get the same point here. That means we can maintain the dryness fraction at the end of the expansion process as from the restriction of the turbine blade, and also we can use the high pressure at the boiler provided we go for a reheat. It is clear? Provided we go for a reheat. That means this is known as reheating. That means we make the pressure expansion in one turbine up to an intermediate pressure, then go on heating it and then again expand it. So this is the concept. That means reheat comes into consideration, that when we can go for a higher boiler pressure but not sacrificing the dryness fraction at the end of the expansion. Clear? Now with this, well, we can straight go to this figure. We see that this is the thing. Here, if you see this figure, you see, just let me first draw this, then it will be understood. Sorry. So this is the condenser pressure. Now this is the boiler pressure, initial boiler pressure. So this is the initial boiler pressure. Well, so this is the expansion part. Oh, I am sorry. So this is the point. Oh, I have shown by a so this is the point. Now we see that. So therefore this is the maximum temperature, Tmax. So this is the point. Now you see here what happens. 1, 2, then 3, or let 3, this is 4, this is 5, this is 6. Now you see what happens. Now see that this is the restriction, that this is the restriction, that is 0.85 line. Let x is equal to x mean, that is the minimum value which we can reach, which is usually 0.85 to 0.9. Now you see here, if we could have dropped from this pressure, we have used a very high boiler pressure. This is the high boiler pressure and this is the temperature. That means if we could have used P1, this is the P1 pressure and this Tmax temperature, and if we could have expanded up to this condenser pressure, this is the condenser pressure, that is PC, then we could have landed here, whose dryness fraction is lower than the x mean. So which is not allowable. So therefore what is done is that it is expanded in to an intermediate pressure. This is an intermediate pressure line. So this is an intermediate, I am doing by a dotted line. This is the intermediate pressure line P2. So up to which it is expanded. The state may come dry saturated, state may come even superheated, it may go here depending upon the value of the intermediate pressure. Here I have shown that this state has just come. If this is the intermediate pressure, after the isentropic expansion it cuts the saturated vapor line. It depends upon the operating conditions that will be told in the problem or in the actual case. Then again it is reheated, that means the cycle is like this, that it expands in the first stage of turbine, then it is again reheated, and then it is expanded. After reheat to the same maximum temperature, it is being expanded to the condenser pressure, and then the rest part remains the same. Follow here that this is the boiler part. Now you see from the boiler this comes here, that means I can give this point as 1. So this is 1. After the expansion from the HP, this is known as high pressure turbine. So this expansion takes place in a turbine known as high pressure turbine, where the steam expands from the initial pressure, that is the pressure of the boiler, to an intermediate pressure much higher than the condenser pressure. So this point corresponds to the point 3, corresponds to the point 2, high pressure. Then it is again heated, and this is a coil, heating coil, which is placed inside the boiler. So it has been shown diagrammatically like that. This represents the water drum or steam drum, where heat is being added and steam actually is being evaporated here. This contains both water and steam, and inside the boiler there are places where the fuel is burned, and these burned gases exchange heat to the water in evaporating it to the steam or vaporizing it to the steam. Then the same burned gases before going out of the boiler is being used to heat the steam coming from the high pressure turbine, which passes through a coil tube, and this is known as reheater. That means it takes heat from the boiler itself, and then this heat, after taking this heat, that means the boiler heat transfer, that means the external heat is now increased. So therefore, because it heats water to vaporize and also to heat the steam from the HP turbine, to heat it to a temperature or the state point 3, these are all 3 points, and this 3 enters to the LP turbine, low pressure turbine. So low pressure turbine inlet pressure is this intermediate pressure, and this is expanded to the condenser pressure 4, and we maintain this dryness fraction. So otherwise, if we could have used one only HP turbine and could have expanded up to the condenser pressure, we could have ended up to a dryness fraction which is more than this. Now here the question comes, well, the basic purpose of using the reheat is that we can go for a high pressure boiler with the same maximum temperature and not sacrificing this. This is because if this has to be respected, this X minimum, then we will have to use this pressure if we have to use this maximum temperature, or you will have to use this pressure if we have to reduce the maximum temperature. Well, but you can use this pressure and also the maximum temperature, provided you reheat it, that means drop it to an intermediate pressure and then again reheat to the initial temperature and then drop it to the condenser pressure. So this is the philosophy of reheating, that we can use a high pressure, a higher pressure in the boiler or turbine inlet and go for a expansion ending at to a dryness fraction which is limited by the turbine blade material. But the question is there that whether this reheat increases the efficiency or not, this question cannot be answered so directly. This is because that depends upon whether the mean temperature of heat addition from 1 to 6. Now mean temperature of heat addition is changed from earlier mean temperature of heat addition was something like 1 to 6 without reheating. Now with reheating, the mean temperature of heat addition will be mean for 1 to 6 and also this 3 to 2. That means the mean of these two mean temperatures, because there is also a heat addition process and 3 to 2. Whether this mean temperature is increased or not, that will determine whether there will be an increase in efficiency or not, and this will depend upon the operating conditions. Now you see what is that. So this is the heat addition process in the boiler. This is QB, and this is the heat addition process in the reheater which is placed in the boiler itself. So practically all this heat transfer takes place in the boiler, but now cyclically we are showing that this is the heat addition process for the water to vaporize to steam, and this is the heat addition for heating this steam from 2 to the state 3. So therefore we can write here the heat addition, the Q addition, heat added, rather I write added per unit mass basis. If I write, then H1 minus H6 plus H3 minus H2. Now this is the heat added, whereas heat rejected which equals to QC which equals to H4 minus H5. So therefore efficiency you can write as 1 minus heat rejected by heat added. In this case the work done in the turbine per unit mass basis can be written as H1 minus H2, that is the work done by the high pressure turbine, plus H3 minus H4, that is work done in the low pressure turbine. So therefore if you can draw the diagram, cycle diagram vis-a-vis this block diagram, so that you can designate all these state points accordingly here and here, then you can recognize the physical processes happening here and corresponding the ideal processes, then you can write all these expressions for thermal efficiency and all these things. So therefore now the question comes that how can we find out. Now for example, now the problem which may be said like that, if you are told the condenser pressure and this dryness fraction at the end of an expansion, then you can find out what should be the this reheat pressure. If it is reheated to the same initial temperature, if you know the initial temperature T1, then you can find out first this point T1 and P1. Okay, then how to find out the reheat pressure? You can draw a vertical line, but TS diagram you don't have. That means you can equate this entropy here and entropy here. That means the same temperature here, that means for example the inlet temperature is 600 degrees Celsius told, and the inlet pressure for example 10 atmosphere P1. So I fix this point. Then at 600 degrees Celsius, now I know this entropy. How? Because I know this dryness fraction limit and I know the condenser pressure. So this point entropy I know. So if we equate this entropy at this temperature in the superheated steam table, I will try to find out at which pressure at this temperature from the superheated steam table this becomes the entropy. You understand? That means I can find out the pressure. Geometrically it is very simple to understand that if I draw a vertical line up in TS plane, this cuts this point, so this is the intersection point. The isobar which passes through this is my intermediate pressure. So this way you can detect the intermediate pressure. Sometimes it is not wise to do these problems with use of steam tables, because so many interpolations and the searching out business takes place, because this entropy same. So I will have to find out at this temperature, this entropy, what should be the pressure. So that is why this is done geometrically the way I have explained in TS diagram, in an HS diagram which is known as Mollier diagram. Sometimes the HS diagram, these problems are solved directly by locating the state points and going like this. So this HS diagram looks like this. In practice this Mollier diagram which is available, HS diagram already we have discussed, but the HS diagram which is available H and S commercially, this looks like this. This is the line x is equal to 1, and you will be having different line x is equal to 0.9, x is equal to 0.8, constant x line like that, x is equal to 0.7, and you will have the constant pressure line like this, divergent line. So this is the constant, as you know the constant pressure line are straight lines but diverging straight lines. These are the constant pressure lines. There are various constant pressure lines like this. So these are the constant pressure lines, that means P1, P2, P3, P4 like that, P5, P6, P7, these are the constant pressure lines. And the constant temperature lines in HS diagram is like this. These are the constant temperature lines. These are the, why I am drawing dotted, these are the constant T line. T is equal to constant. T is equal to. So this line bifurcate only from this. You understand? Only from this point. Why? In isotherm like this. This is like this, and within the vapor dome constant pressure line is the constant temperature line. For example, if I designate this pressure line as the P is equal to 1 atmospheric pressure, this pressure line, that means it meets an isotherm. So this isotherm will be what? This isotherm will be 100 degrees Celsius. So 100 degrees Celsius isotherm is this and coincides with this, and this becomes the, this pressure is the 1 atmospheric pressure. This pressure is the 1 atmospheric pressure. So this is typically the diagram, this is known as Molière diagram. Now if we know the condenser pressure, for example, if we know the condenser pressure and this is my point, this is the condenser pressure PC and my dynamitization is limited by point A. Okay, and I know the initial temperature and initial pressure here. So how can I find out the initial temperature is this much, this line, and initial pressure is this. This is the P5, this is the initial pressure. So this is the initial temperature line, so this is the initial this I will read H. The initial temperature line. Now from this dynamitization I will have to go straight to this point which will cut the initial. That means this P4 will be then my intermediate pressure. That means I can draw this cycle now like this. I can draw this cycle on HS plane like this. This will be then made like this. You understand? So that if I can draw this, I can read all the points. This is the same temperature. I can read this point, I can read this point, I can read this point. So directly we can get enthalpy. That means we can construct the process on the HS diagram. So it is very easy to find out the reheat pressure and HS diagram, that I draw the isentropic line straight. It cuts the same temperature line. Let this is equal to 600 degrees Celsius. That P5 is 10 atmospheric pressure. So this is my inlet point 1. So this is the constant pressure line. Now if it is told that it is expanded up to the disaturated condition, which is usually made in practice, then my 1, 2 point is there, then this is my 3 point and this is my 4 point. So 1, 2, 3, 4 process, that is the expansion in the high pressure turbine, reheat, and the expansion in the low pressure turbine, I can do it here. So that directly I can find out H1, H2, H3, okay, H4, we can read it and we can get the value. It is more wise to use this diagram than this stream table. But a request is that before the examination you must have a practice with this diagram, so that day of the examination if you have to solve with this, then you may find difficulty. So that you will have to see how does it look. It looks like this and you have to solve 1 or 2 problems using this diagram, where you can straight away locate these state points. Alright, this is about reheat. Tomorrow I will solve a problem on reheat and we will start another new thing, that regeneration, concept of regeneration. Okay, thank you.